the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to linear algebra students and possibly pre-calculus students who are currently going through matrix algebra. And you should have already watched my videos or be very familiar with matrix algebra itself, specifically the arithmetic of matrices, how to add them, subtract them, multiply them, but not divide them because there is no such thing as division of matrices. This video, we're going to focus on the inverse of a matrix, specifically the inverse of a 2x2 matrix, because it's a huge topic. That is, inverses are a huge topic in matrices. And so we want to take our time stepping into that topic. Put a little note here. Up to this point, we've been able to do almost all arithmetic operations on matrices with some odd caveats. For example, matrix multiplication works, but is not commutative. That means that in general, A times B is not equal to B times A. The only operation we've avoided thus far is the inverse of multiplication, which is commonly known as division. However, division in a very strict sense is non-existent when it comes to matrices. Multiplication by the inverse of a matrix, however, is sometimes possible. So we first have to start with a definition so we can all speak the same language when it comes to talking about the inverse of a matrix and whether a matrix is actually invertible. What does that even mean? Well, an n by n, or a square, that's very important, that A be a square matrix. So an n by n matrix A is said to be invertible if there exists another square n by n matrix denoted A with the superscript notation there, which is a very unfortunate notation, but we'll just go ahead and call it A inverse, such that when you multiply on the left the matrix A by this brand new matrix we're calling A inverse, that product will be the same as the product had we multiplied on the left by A inverse first against A, and that product should be the identity matrix. In fact, both of these products, because they're equal, will be the n by n identity matrix. That's if A is invertible. If there is such a matrix that when you left and right multiply it against A, that it becomes the identity matrix, we would call that matrix A inverse. Now, a little bit of a warning down below in red. While it might be tempting, please do not write A inverse B as B over A. Better yet, don't even write it as 1 over A times B, because that is not true. This notation is undefined in mathematics and encourages mistakes. And I should say this notation, when it's applied to matrices, is undefined in matrix algebra. So do not think of A inverse as 1 over A. It's just not. There's no such thing. Now that we've defined what it means for a matrix to be invertible, that it would have another matrix that when left and right multiplied, it becomes the identity matrix, we're going to add into our language a couple other words here, and they just creep up into a lot of math textbooks, so it's a good idea just to define them right now. A matrix that is not invertible is called a singular matrix, and an invertible matrix is called a non-singular matrix. Now, to be very honest with you, I don't use the phrase non-singular matrix very often. However, I do use the phrase singular matrix a lot. When you have a matrix that's not invertible, that is a singular matrix. And here's where I can draw an analogy with arithmetic. 0 in arithmetic, and pretty much in all of mathematics, is kind of an obscure concept. It's a very special number in arithmetic because while other numbers in arithmetic, like 3 and 7, they have multiplicative inverses, 0 does not. So by this kind of result that 0 does not have an inverse, or in other words, 0 is not invertible in arithmetic, you might think of 0 as a singularity. That is a singular number. And while that is not actually how we would define it, it's very close to actually how we would define it. So that is a good way to think about it. There's a singularity because if you try to take the multiplicative inverse of 0, first of all, you don't know what the numerator is. It could be 5, it could be 1,000, or it could be 1, or it could be -1. But worse yet, you can't actually divide by 0 because that's called undefined. So that is a singularity. Anyhow, it just pays to know that when you have a matrix that's not invertible, we would call it singular. All those definitions out of the way, let's go ahead and dive into an example. We're going to show that the following two matrices are inverses of each other. That is, A has the inverse B, and that B actually has the inverse A. Now remember, if B is the inverse of A, then we want A times B to equal the same thing as B times A, which would be the identity matrix. Notice in this case, it looks as though I'm saying that matrix multiplication is commutative. Normally it is not, and in fact, it rarely ever is. However, this is one of those special cases where it actually might be. So let's take a look at that matrix multiplication very quickly. I'm assuming that you've actually already gone through what matrix multiplication is, so I'm not going to take my time with this. I'm just going to run right through the multiplication. However, I did write out the arithmetic there just so that you could see how I got my numbers. So I did say I wasn't going to show it, but there I have. Well, it sure does look like A times B is the identity matrix. That does not, by the way, mean that B is immediately the inverse of A. That is actually not true. You have to actually show the other multiplication, B times A, is also the same sized identity matrix. So let's go ahead and do that. And there we have it. B times A is also the identity matrix. So therefore, and by the way, it's the 2 by 2 identity matrix in both cases. Therefore, A times B is equal to B times A, which is the identity matrix. Thus, B is the inverse of A. And actually, by the same argument, if you reordered this and talked about B times A equaling A times B is equaling to the identity matrix, we will have shown that A is the inverse of B. I'll just write that down below. And there we have it. B is the inverse of A, and A is the inverse of B. And that's all I really wanted to do in this video, was to introduce the idea of an inverse, what it actually is. I haven't shown you how to compute an inverse yet, but I don't think that's important for your first introduction to inverses of matrices. It's just important to learn, what does it mean for two matrices to be inverses of each other, and what does that mean when you multiply them? And then we got some language down as well. Now that we've gotten that out of the way, in the next video, we'll talk about how to actually compute the inverse of a 2 by 2 matrix. Only a 2 by 2 right now, because as you grow to larger matrices, it gets a little more complex. I hope to see you there. I hope you have a wonderful day and that you're a good human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.